Yeah, hello. Can you hear me well? And do you see the presentation?
Yes, yes, perfect.
Yeah. Thank you for the invitation. So yeah, today I will talk a bit about some challenges and gaps and what we're doing here at JRC regarding the life cycle environmental impacts of hydrogen. Yeah, so a bit of context. Yeah, in 2022, it was already presented, the Repower EU had very ambitious goals for 2030, about 20 million tons of renewable hydrogen. Now these targets are being revised, but already in the Repower EU, they were mentioning that a life cycle approach is needed to minimize the negative environmental impacts of the hydrogen sector, and that we need reliable methodologies to assess the environmental impacts of hydrogen along the whole value chain. And in 2024, I mean, now these targets are being revised, but still hydrogen will have an important role. And you can see in the political guidelines for the new commission, and where it was mentioned that we will invest in the deployment of a hydrogen network and in green hydrogen production. So the work we did at GRC was to try to identify the EU legislation that we have at the moment, and also internationally that are mandating the assessment of environmental impacts of hydrogen, and then try to identify discrepancies and gaps that are across these legislative requirements, and then to provide recommendations to the policymaker in Brussels and in general on how to improve the current gaps. So if we see the European legislation that is touching on hydrogen and is requiring a greenhouse gas emissions assessment or assessing environmental impacts, there are quite a few. We can see we start from the taxonomy, which is the aim is to define which hydrogen production pathway can be qualified as sustainable for sustainable investments. Then there's the Renewable Energy Directive that was presented by my colleague this morning, Marco, with the goal of defining when hydrogen can be considered a renewable fuel or a biofuel and its associated life cycle greenhouse gas emissions. And there's the emission trading scheme and the new carbon border adjustment mechanism that with the goal of taxing hydrogen production methods according to their associated greenhouse gas emissions. And then there are guarantee of origin and other certification schemes that are used to certify the origin, the sustainable origin of hydrogen. And then there are various funding schemes within the EU, such as the Innovation Fund, the Important Project of Common European Interest, and that their goal is to support the development of sustainable hydrogen technologies. And each of these pieces of legislation have their own reference guidelines for assessing the greenhouse gas emissions. And due to the different scopes of this legislation and the different development processes, these guidelines may differ between one and another. So for instance, the taxonomy refers to the Renewable Energy Directive or the ISO 14067 and the 14064 for the assessment of the greenhouse gas emissions, the Renewable Energy Directive for renewable fuels of non-biological origin has its own delegated regulation for assessing the greenhouse gas emissions. The CBAM is now the guidelines are now being produced and they're not finalized yet. And then the guarantee of origin and the funding schemes, they usually have their own ad hoc methodologies for assessing the greenhouse gas emissions. What are the risks? So for instance, if we take hydrogen production pathway that involves a co-production, like in this case, like chloralkali, the chloralkali process, and you need to give a value for the carbon footprint of hydrogen. So what is the greenhouse gas emissions that is associated with the production of hydrogen from this pathway? Depending on the methodology and on the guidelines, you could obtain very different results. And here I included also the first bar is the ISO 19870, which is a new ISO standard with it's not final yet, but it's the goal is to provide a methodology for assessing the greenhouse gas emissions of hydrogen production. And then you can see that depending on the methodology, also within the EU, we could have very different carbon footprint associated with this hydrogen production. And the multifunctionality can be solved depending with the energy allocation, economic allocation, and so on. And the different methodology may recommend one or the other approach for solving this multifunctionality. So the first challenge is the risks that are due to these discrepancies that could lead to inconsistencies across different policies. It could lead to market distortion because you could promote a certain production pathway because in one case it's considered sustainable. And this could lead also to suboptimal solution in terms of environmental impact because there could be some climate consequences of this market distortion. And then, of course, it could create confusion, higher cost, and skepticism around the life cycle assessment due to these different results obtained with the different guidelines. So what we recommend, and we also published a paper on this, is to have more consistency across the EU and also global policies, like, for instance, this new ISO standard on the methodology to assess the life cycle greenhouse gas emissions of hydrogen. And also, in particular, as I shown in the example, there should be a consensus on how to address the multifunctionality, which is an issue in general of life cycle assessment and not specific for hydrogen. And it would be good if for each pathway it was decided which is the ideal approach, and ideally would be the one that maximizes the policy's efficiency and therefore the minimization of the greenhouse gas emissions from the sector. The other challenge we identified was the limited scope of most of these guidelines. That most of them, they focus solely on climate change. Here I provide just two examples. For instance, this new ISO standard or the delegated act in the EU for renewable fuels of non-biological origin, and they both focus solely on climate change. And but as you know, like the environmental problems we're facing at the moment are much bigger than that, and there's the risk of, if we focus on climate change alone, to shift the burden, the environmental burden, to other environmental impact categories or to other social consequences that are not included in the methodologies. Here I reported a figure of the planetary boundaries, so you could see that where some environmental impact categories that are really important to address at the moment, such as biogeochemical flows like eutrophication and land use, water use, or the biosphere integrity. And so the recommendations we provide is to have methodologies that take into account a broader environmental impact, so a holistic approach. In the EU, we have already a methodology that does that, is the environmental footprint method. And you can see on the right a list of all the impact categories that are included in the environmental footprint method. There are 16, and they include acidification, climate change, ecotoxicity, and so on. And also we believe that these methodologies should also take into account the social implication of the hydrogen technologies and to extend beyond the environmental sustainability to include also social and the economic as well. The third challenge we've seen is the hydrogen losses. It's probably a minor problem compared to the other two, but hydrogen was found to contribute indirectly to climate change as well, because it increased the lifetime of other greenhouse gases that are present in the atmosphere, such as methane, ozone, and water vapor. And the current LCA method, the current guidelines that we have in Europe, but also globally, they don't take into account these emissions and this contribution to climate change. So the EU organized a workshop a couple of years ago on this topic, and we published a report where we summarized the main outcome of this workshop. And the risks of not including these the hydrogen losses in the LCA is to, of course, to reduce the accuracy of the estimates of the impact of the technology we're studying. And also we may have unfair comparison when we're comparing two different technologies that may have very different emissions of hydrogen. So our recommendations on this is to start monitoring, because to start developing the tools to monitor and report the hydrogen losses across the value chain, and then to integrate these hydrogen emissions also into the IPCC models, and develop a consensus around the global warming potential of the indirect global warming potential of hydrogen. And then once there is this agreed upon hydrogen GWP, to integrate it into the LCA methodologies as well. So here I provide an example of a study we did recently at the JRC, where we tried to overcome all the challenges I mentioned. And we tried to estimate what is the environmental impact of transporting hydrogen over long distances. In this case, we consider 2,500 kilometers from Portugal to the Netherlands. And we compare the environmental impact of using different carriers for transporting hydrogen. So we consider compressed hydrogen, liquefied hydrogen, ammonia, LHC, methanol, and synthetic and natural gas. And we also compare it to on-site SMR or electrolysis. And here you can see the results that do not take into account just climate change, but all the 16 environmental impact categories that are covered by the environmental footprint method. And we also included the climate change impact from hydrogen losses along the supply chain. And what we could see is that there are some clear winners, like liquid hydrogen and compressed hydrogen transported by pipelines. But like for other carriers, when we expanded the scope and we include also other environmental impact categories, we could see that the environmental advantage compared to more traditional technologies like on-site steam methane reforming would not be so clear. And so that's why we think it's very important to also consider other environmental impact categories. And what we're trying to do also to consider the social implications of these technologies. In this case, for the hydrogen delivery, we try to look at, for instance, at child labor, economic development. These are just two of the indicators that we consider for the social assessment. And now we're also trying to include potential accidents along the hydrogen supply chain, and to include how these emissions during an accident could affect the sustainability of the different carriers. So for instance, if you have an accident at the port, there's a big difference if you have an accident when you're using ammonia or when you're using hydrogen. So as a summary, so we all know that hydrogen is needed for decarbonization, but we need the right tools to monitor its environmental impact and social as well. And we identified three main areas of intervention to improve the current guidelines we have for life cycle assessment. One is to harmonize the inconsistencies like among the different methodologies. This is valid within the EU, but also globally. If we need to trade hydrogen, we need to agree on the methodology we use to assess the environmental impact. And the other areas of intervention is the limited scope that is currently focusing only on greenhouse gas emissions, but we think we need to expand it to more environmental impact categories, and then to account also for hydrogen losses occurring along the supply chain. So we need the recommendation is to have, I think we believe there's an urgent need for an LCA methodology that allow for the effective achievement of the policy goals that we have in Europe and the world on hydrogen. And these methodologies should be harmonized, strictly defined, should have a broader scope, and should account for hydrogen losses. And, yeah, thank you very much for inviting me, and and for listening. If you have any questions, thank you.
Yeah, thank you a lot for this presentation. Maybe while waiting for questions from the audience in the chat, I could ask a bit about the choice of using the single score method in LCA compared to just presenting for different impact categories.
Yeah, so I just wanted to show it here. Of course, in the report, you can see the results for all the 16 environmental impact categories. But I think providing a single score, I think it can be dangerous because you need to understand what's behind how you arrived to this single score. But I think it's very effective when you have to provide show a figure to the policymakers that have a more holistic overview of what is happening on the environmental impact. So that was the reasoning behind that, because sometimes policymakers are just asking one number and the single score is helping in that direction. Then of course there's a long explanation behind that number, but I think it's good to visually to show the results.
Yeah, thank you. I think there are no questions yet, or is that
yeah, there aren't questions so far, but I would kindly ask Alessandro to keep an eye on the Q&A tab, because so far many questions come after the speaker slot, so it would be really helpful if he could respond to them directly in the thread. Thank you.